Namaste and welcome to Real Multimedia Studios. In this session, we'll be trying to explain a part of a design of machine elements 1, basic concept of a stress, strain, bending and torsion. So, the concept stress. You know well that when I say a word stress, definition of a stress is a vital role. As mathematically, somewhere it looks like sigma is equal to P by, where sigma is equal to in denomination used for stress. Surely you can check in that the same equation being replicated with the pressure, but that doesn't say that stress and pressure are same. There is a quite a lot of difference between a stress and a pressure. To understand that, I like to illustrate one such small example. So just off, I add in a material, a bench made up of a wood as a material. What I do is I will allow one person to sit on this. If wood has a ability to speak, it would say that I will resist this load. Considering that this person is in a load, the wood would say, yes, I will resist the load what has been applied on me. What I do is I will be adding up one more person on it. I'll ask him to sit over there. Wood says, yes, I am ready. Still, I can resist the load. One more. In a similar way, would have been said, I would. One more. One more. Then one more. Now would have been very in a way saying that I could still resist the load. Now one more. Doing this, they would have given up. So here I would like to correlate this example to the definition stress, stating that ability of material, in this case a wood is in a material, ability of material to resist the load would be a definition of a stress, where the stress is an internal property of any material, but when it comes to a pressure, it is an external part of a material. So next would very important is to understand what is strain. I will be taking up one small example, considering a bar, and I will be going apply up within a tensile load on the either side. Doing so, the bar undergoes deformation. The deformation sends out if this upper bar would have a length of, just imagine an L. Now the below one would exceed a bit of with taking as an example of dou L, or even if I take this as a capital L, this would be a small L, capital L would be a original length of a total bar, and a small L would be the difference or the deformation would be taken by the bar when it has a tensile pull all across. So while doing this, whatever the equation that we get would be strain is engine length divided by original length. This is how to correlate the stress and strain. Now coming to the next part, how do I check out with the stress strain diagram, for which again I will be taking up one example, a dog bone specimen under a tensile load. So consider this particular dog bone specimen within a tensile load all across. While doing this, the whole specimen tends to pull and undergo a deformation. So for this deformation, I like to explain with this curve what I said as a strain curve. So this is a strain on the x-axis and stress on the y-axis. I can see here as the load has been applied, there is a linear increase of stress and strain. So this part of the graph we call it as an elastic region. The rest of the part we call it as a plastic region. So in an elastic region, if the stress is directly proportional to the strain, that would refers the Hooke's law. So once it moves above the point of a elastic region, what you see over here would be of yield stress. So further it enters the plastic region, and at the last the specimen breaks at this point. So that point would be an ultimate strength of this material which has been undergoing there, as you see a dog bone specimen under tensile. So next would be, I will be correlating how this ductile and then a brittle deformation will take place in a material, for which I like to take this curve as an example. As you can see over here, first curve states up a ductile material, second one states up a brittle material. So the ductile, you can see that there will be a deformation of plastic will be taken care of over here, but when it compares to this, there won't be any plastic deformation. So if it is a ductile, it will undergo a plastic and elastic and a plastic deformation, but brittle just goes off and gives off there will be a breakage of a material. I like to correlate the same thing with a better example. Taking up, if I say as a brittle material, yes, it's a very important element that if I take an example of a chips. Chips is the one which gives off a metal without any plastic deformation. Just to have a break, put a load on it gives off. So that's the best example when I go with a chips setting as it's a brittle in nature. So what would be the ductile in nature? I can see a lady has been chewing up the chewing gum and she pulling it down into a tin wall. So this refers to ductile. So if at all this thing is need to be within a material, yes, the upper one is in a deformed undeformed block. When it has a brittle one, goes off without any plastic deformation. When it comes to a ductile, you can see here that it undergo a plastic deformation, then turn out to be into a thin wire and then gives off. So this is a relation how the ductile and brittle goes across. If I take an example of a material. So somewhere around in a world of engineering, this brittle and ductile plays a vital role. We want like a chip to be in a ductile nature or a gum into a brittle. So chips need to be in a brittle and a gum need to be in a ductile way. So next is how would I correlate the bending stress? As you can see over here, there is a shaft being supported with the two elements over which I had a load applied. So as the load is applied there, the whole shaft undergo a deformation, and you can see in a red mark quite below what's the deformation of bending happens up when it does it. So here in a future forthcoming chapters, I will be clearly letting you know how bending stress works in. But here, as if I will be database pulling it down to the bending equation. Like bending equation comes out like m by I, f by y, and e by r, and whereas sigma b will be in a bending stress, which will be equal to m by z, where z is equal to I by y. And to elaborate it down in a way where m would be the bending moment as is shown over here, and I is in a moment inertia, and the sigma would be in a bending stress. In the case here, I written that in terms of sigma of b, and in y and c would be the distance of a centroid fiber and the neutral axis. E would be in Young's modulus, and r is the distance of curvature. And in another important criteria in design of an element would be a torsion. So torsion comes to at one side if I fix a point, and another side, as you could see over here, the rotation has been taken care. So this is in theta. So if this happens, it undergo the whole beam will undergo a torsional. Even you can call it a torsional reference. So for which the equation would be torsional equation would be T by g theta by L is equal to tau by R, where tau would be the shear that may happens due to the torsion. So it would be TR divided by L, where T would be torque, R is radius of curvature, J is a polar moment of inertia. So this is a basic concept of a design of machine elements when it comes to stress, strain, bending, and torsional one. So in our next issue, we will go ahead with some more information regarding this of machine elements. Till then, take care, be safe, and keep in touch with the SDM multimedia studios. Thank you.